Hi, my name is Sathvik, and a student at Thomas Jefferson High School, along with my co-authors Jagadeep Madipatla, Pranav Day, and Anand Khandelwal. I'll be presenting the Programmable Optoelectronic Hardware Accelerator for Ultrafast Tensor Arithmetic, both a software and hardware multifaceted approach. So, a quick background. The AI gold rush, the exponential boom that we've seen in data growth over the past specifically maybe 10, 20 years, it's leading to a high demand of linear algebra computations. As neural networks are becoming more and more prevalent, the high amount of computations that are required to run them are also skyrocketing. At the same time that this is happening, however, Moore's law and Dennard scaling are both beginning to decline, flatline even. And as they flatline and the growth in AI demand skyrockets, we're seeing a disparity. We need to raise the computing capabilities from flatlining to also growing with the demand of linear algebra computations to create a way forward for the future of AI. Now, if we see traditional approaches like CPUs, GPUs, and even TPUs, these are traditionally how neural networks are run or how AI processes are handled with this traditional electronic hardware. However, all of these hardwares depend on microscopic devices known as transistors, and we're fundamentally seeing a limit in how small transistors can become. Since transistors can no longer become smaller, we're no longer able to access further and further compute capabilities. Therefore, we need to find non-transistor dependent approaches. And on top of this, the software that's resting on these faulty transistor dependent systems is also going to be rewritten once we find a new alternative approach, which crumbles down the software stacks that literally everyone is using around the world that depends on these transistor dependent architectures. Therefore, we need to find a solution and we need to find it quickly. The solution that we propose is a custom linear algebra hardware that's not tied to Moore's law. It's not transistor dependent. And therefore, it is no longer limited to the flatlining growth that we're seeing over the past few years. And the software that's able to run complicated linear algebra requests on this analog hardware, this non-transistor dependent hardware, is also no longer tied towards Moore's law. We have a clean integration into a multifaceted hardware software approach, a non-transistor dependent chip, and also a software stack that runs on this non-transistor dependent chip.
This is our solution to the problems listed earlier, the Tachyon NPU. The NPU is an analog computing unit capable of processing vector matrix multiplications at the speed of light. While CPUs and SIMD units like GPUs process matrix multiplications by each element, the NPU processes the entire 2D matrix at a time. Here is an example render of the chip in QFP format. Below that, you can see a table with basic chip statistics for a 4x4 matrix operation and a larger 256 by 256 matrix operation. The operation performance continues to scale for increasing sizes of matrices and also scales for performance per watt. The chip's clock speed goes down as the matrix gets bigger. This is due to the sharp rise in input data size. Each element is represented by an 8-bit value, leading to a sharp increase in the time required to load the chip. This drop can be reduced with an optimized interconnect. The bottom right includes a table with part of an instruction set. Here we have a diagram of instruction flow. The neural network model informs the Apollo programming language code. The code is sent to be interpreted by a custom software stack consisting of a virtual machine that interfaces with the accelerator hardware. Results are then sent back to the host. The architecture allows for many different configurations. Multi-dimensional tensors can be broken up. Different sized matrices can be arranged into blocks and padded with zeros as necessary, and users can choose between many different operations shown here. All of this is taken care of by our custom software stack and interfaced with the hardware in the right format. The NPU computes its operations using modulators that shift the phase of light. Each phase change is defined for an operation. The modulators take an analog voltage input that corresponds to different angles. These specific angles are stored in a lookup table. When a matrix vector multiplication is requested, the required phase angles are parameterized and the corresponding voltages are looked up to be sent to the accelerator hardware.
So essentially, we created an extremely efficient tensor storage framework catered to our optical hardware that has the benefits of both the CSF framework and the COO framework. And this is seen more clearly in the table to the left with respect to the required memory and the time complexity of the matrixization process, which is O of 1. As you can see, our format has the benefits of both CSF and COO. Furthermore, with respect to the memory efficiency, it's clear that over 10,000 trials of 1,000 sparse tensors, our format once again performs much better compared to the alternative frameworks in the market and is in fact able to keep on par with the CSF framework. So essentially, this is extremely significant, specifically when it comes to the rapid growth rate of AI that we've seen in the past few decades. Raising compute capabilities is a necessity to make sure that generative AI and large language models are able to be researched into in the coming years. Essentially, furthermore, we introduced a big jump in linear algebra computational efficiency through a hardware software approach. We created a programming language that's able to run tensor algebra on optical hardware. We created a virtual machine, allowing tensor algebra code to run on any matrix processor. And we introduced a new way to store sparse tensors designed for matrix processors, which once again retains the benefits of both the CSF and COO formats.